When you hear AC/DC, you probably think of the rock band, but the AC/DC we're going to talk about today is alternating current and direct current. Direct current is commonly used in things that use batteries. Direct current has a constant voltage source and a constant current flow in only one direction around a circuit. Alternating current, on the other hand, does not have a constant voltage source, and the current switches directions. For example, in one circuit, the current is flowing in a clockwise direction. After the direction switches, the current will be flowing in a counterclockwise direction. One way we can visualize this is by graphs. This first graph, for example, is DC current. The voltage remains constant, and the current remains constant. This second graph represents AC current. The voltage is constantly changing, and the current is also constantly changing. V naught is represented here as the peak voltage, and I naught is represented here as the peak current. This second graph can be represented by the equation V equals V naught sine 2 pi ft, where V is the voltage at time t, V naught is the peak voltage, and F is the frequency in hertz. Because of the relationship V equals IR, this equation can also be shown as I equals I naught sine 2 pi ft, where I is the current at time t, and I naught is the peak current. So, using this equation, we can determine the peak voltage of AC power. If the voltage is measured to be 67.07 volts at t equals 2, what is the peak voltage given that the frequency is 60 hertz? To start off, we'll use our equation V equals V naught sine 2 pi ft. Once we add in our values, we simplify it to 67.07 volts equals V naught times sine of 2 pi times 60 hertz times 2 seconds. If we simplify that equation further, we get 67.07 volts equals V naught times 0.55893. Solving for V naught, we end up with 120 volts. We can see uses for DC power all around us. Batteries are a common example of a DC power supply. Other common everyday items that use DC power are cell phones, flashlights, cars, TVs, and even solar panels. We can also see uses for AC power all around us. Most outlets in homes and buildings use AC current. AC current is used instead of DC current because it uses high voltage, allowing the same power to be transmitted at lower currents. AC can then be converted from a high voltage to a lower voltage to be used in the home by a transformer. With DC current, a lower voltage is used, making the current higher to transmit the same power. Because a higher current is used, more energy is lost in transmission. Because AC switches directions, there is a small moment where the power supply is not active. In a circuit with a light bulb, this means that every time the current switches directions, the light bulb turns off. You may be wondering why a lamp or a light that is plugged into an AC power supply doesn't flash on and off. While you may think it doesn't, you just can't see it. In North America, the AC power supply in our homes is 60 hertz, which means that it changes direction 60 times per second. This is so fast that you perceive the flashes of light as one continuous supply of light. To demonstrate this, I have two different lights. This flashlight is powered by a battery, which is a DC power supply. This strand of Christmas lights is plugged into an outlet and powered by AC power supply. To demonstrate this, when I swing this flashlight around on a string that is powered by a battery, which is DC power, you see a continuous circle of light, as shown here. On the other hand, when I swing the strand of Christmas lights in a circle, you can see that it isn't a continuous circle of light. You can see the small gaps in the circle demonstrating the switches in direction for the current. This is showing the switches in the current direction that are found in the AC power supply.